I want to tell you about the most powerful thing in this whole series. And then, in the very same breath, I have to tell you it might be doomed. Everything you and I have built together, the qubit that can face any direction at once, the interference that makes wrong answers erase themselves, the entanglement that ties distant coins together with an invisible thread, all of it, every scrap of the magic, runs on one single quality: delicacy. A quantum state is the most exquisitely, heartbreakingly sensitive thing we know how to make. And here is the sentence that has been lying in wait for us since the very first night, the one I've been quietly dreading. The universe is always watching. And the instant it looks, the machine dies. Tonight, at last, we meet the enemy, the gift that is also the wound.
The enemy. Yes, and I've been dreading tonight too, if I'm honest. Because for 6 episodes now, you and I have been falling a little in love with this thing. And tonight, I have to show you the crack running straight through the middle of it. But I want to be truthful about where the crack comes from, because that's the whole tragedy of it. It is not a manufacturing defect. It is not sloppy engineering that some clever person will tighten up next year. The fragility is the flip side of the power. They are the same coin.
Say that more slowly because it already unsettles me. I'd assumed the fragility was, a bug, a rough edge the engineers would sand down eventually.
I know. It would be such a comfort if it were. But cast your mind back to what made a qubit special in the first place. A plain, ordinary bit, the kind in the very device you're listening on, is a bruiser. It's stored as billions of electrons piled onto a tiny patch, either a puddle of charge sitting there or no puddle. You can kick it, warm it, jostle it, and it just shrugs. If a few thousand electrons wander off, who cares? There are billions more, and the puddle is still plainly a puddle. It is sturdy precisely because it is crude.
And a qubit is the opposite of crude.
A qubit is a soloist. Very often, it is one lonely thing. A single atom, the spin of a single electron, one faint whisper of current going round a superconducting loop. And it isn't holding a nice fat yes or no. It's holding a direction, that arrow on the sphere we drew back in the qubit episode, free to point anywhere it likes, its entire meaning living in the exact angle it holds. That is a fantastically rich thing for one tiny object to be carrying. And anything rich enough and small enough to carry all of that is light enough for a single breath to knock flat.
So, the very thing I admired, one tiny object holding this whole smooth, continuous direction, that's exactly what makes it a pushover.
That is the wound folded inside the gift. You wanted a thing sensitive enough to feel the difference between pointing here and pointing a hair to the left, because that sensitivity is where every last drop of the computing lives. But a thing that sensitive feels everything else too. It cannot tell the difference between you nudging it on purpose and the universe nudging it by accident. To the qubit, a nudge is just a nudge. The environment is always watching.
All right, you keep saying the universe is watching. It's a lovely, spooky phrase, but I want the real thing underneath it. What is literally happening to my poor qubit?
Then let's go back to the single most important idea in the whole quantum story, the one we broke our heads on in the measurement episode. When you measure a quantum thing, you force it to commit. The spinning coin that was genuinely in a blend of heads and tails clatters flat and picks one. The superposition, gone. You remember how strange we both found that.
I remember it ruined my week. The looking is what does the damage.
The looking is what does the damage. Now here comes the blow. It does not have to be you. It does not have to be a physicist or a laboratory or some measuring device with a dial on the front. Anything that interacts with the qubit, anything at all that comes away carrying so much as a whisper of information about which way that arrow is pointing, has, for every purpose that matters, measured it.
Define anything for me. I want the actual culprits.
A stray photon of light glancing off it. A single molecule of air blundering into it. A faint tremor of heat in the material cradling it. A wandering magnetic wobble from a wire 3 rooms away. Each of those is a tiny interaction. And in each one, something out in the wide world, the photon, the molecule, the surrounding stuff, bounces off your qubit and flies away subtly changed depending on what the qubit was doing. It flew off one way if the arrow pointed up, and a different way if it pointed down.
So that photon is now carrying the answer away with it. It's a little witness.
It is a witness, and it has bolted off into the room with what it saw. And here is the part that ought to raise the hair on your arms. Remember from the entanglement episode that when two quantum things interact and become correlated, they get tied together. Entangled. Well, that is exactly what has just happened. Your qubit and that fleeing photon are now entangled. The photon knows which way the arrow was pointing.
But nobody read the photon. It just sailed off into a wall. Nobody in the entire universe checked what it saw. Surely that can't count as a measurement. Nothing was recorded. Nobody knows a thing.
That is the exact objection every single person makes, and it is the beautiful, terrible heart of the whole matter. It does not matter in the slightest whether anyone reads it. It only matters that the information got out. The very instant that which-way fact is out there in the world, smeared onto a photon halfway into the plaster, a photon you could never chase down and reel back, the qubit's superposition is finished. Not because anyone learned the secret, because the secret leaked.
Wait, why should a secret leaking, with nobody on the other end to hear it, break anything at all?
Because, and this is the thread from the very first episode, come back to haunt us, information is physical. We spent a whole night on that idea. Information is not some abstract nothing, it is a real physical thing that lives in the arrangement of the world. And a superposition is only alive, only able to do its quantum magic, for as long as which way the arrow points is written down nowhere in the universe. Not recorded, not encoded, not smeared onto a single passing photon. The moment that fact exists anywhere out there in the world, the qubit stops being a genuine living blend and becomes just a dull, ordinary, well, it's one or the other, we simply haven't checked yet. And that ordinary thing is no earthly good to us.
So the coherence, the quantumness, it isn't so much destroyed as it escapes. It bleeds out into the surroundings.
It leaks. That's the truer word, and it's kinder to the physics too. Nothing was smashed. The delicate quantum information didn't evaporate. It fled. It ran out of your little qubit and spread itself thin across a trillion jostling specks of the environment. And in principle, it is all still out there somewhere. But in principle is a cruel little phrase. To win the magic back, you would have to round up every last photon and air molecule and ripple of heat that ever so much as brushed against your qubit, and unjostle every one of them in perfect reverse. You cannot. Nobody can. And a thing you could never ever reverse is, for every purpose that will ever matter, simply gone. That leak, that quiet one-way bleed of quantumness out into the world, has a name. Decoherence. And it is the enemy of this entire series. Why the answer dissolves.
I want to feel why that's fatal for computing, not just for one lonely qubit sitting in a box. Because in the interference episode you sold me, completely, on the real magic being interference. Wrong answers cancelling each other out like waves, so the one right answer is left standing alone. What does the leak do to that?
It goes straight for the throat of exactly that. Let's use the picture that started it all, the wave that travels two ways at once and then comes back to meet itself. The whole reason interference works, the entire reason, is that the two paths are indistinguishable. There is no fact, anywhere in the world, about which one the wave really took. And precisely because there's no such fact, the two paths overlap and they can cancel. That cancellation is the whole trick. That is how a good algorithm arranges for every wrong answer to meet its own mirror image and wipe itself clean out of existence.
Right, the cancellation is the machine. That was the thing I carried out of that episode.
Now let the environment tag the paths. Let one stray photon come away, carrying, "It went this way, not that way." You have just created a fact in the world about which path was taken. And the instant that fact exists, even unread, even lost forever inside a wall, the two paths are no longer indistinguishable. They cannot cancel anymore. It's exactly like the double-slit experiment we all love so much. The moment you can tell which slit the particle sailed through, the beautiful stripes of light and dark simply vanish, and you're left staring at a dull, meaningless smear.
Oh, that's horrible. So the environment doesn't smash my computer to bits, it just spoils the interference. It tags the paths, so the wrong answers quietly stop cancelling.
And if the wrong answers stop cancelling, what do you suppose is left?
They're all still there. Every wrong answer, unerased, still shouting at the top of its lungs. My careful, delicate arrangement, where only the right answer was meant to survive, it collapses straight back into noise. A wash of every possible answer at once, with the true one no louder than all the lies.
That is precisely it, and you reached for the word yourself. Noise. That is why we call the enemy what we call it. Decoherence doesn't politely delete your calculation. It drowns it. It takes the exquisite, hand-sculpted pattern of amplitudes, the one where you painstakingly set things up so the truth reinforces and the lies annihilate, and it lets the lies back in, one leaked photon at a time, until the sculpture is mush. The answer you are computing is still nominally in there, somewhere, buried under a rising tide of uncancelled garbage. And every fraction of a second you let slip past, the tide comes in a little further up the beach. Why your coffee cup is safe and your qubit isn't.
Here's something that's been nagging at me, though. If the universe is this trigger-happy about measuring things, if a single photon glancing off is enough to collapse a superposition, then why isn't everything collapsing all the time? Why can a qubit hold a superposition for even a sliver of a second, while my coffee cup is never in two places at once? You've told me, more than once, that the quantum rules apply to everything. So where on earth is the coffee cup's superposition?
You have just asked one of the very deepest questions in all of physics, and the answer is the most bittersweet thing I will hand you tonight. Your coffee cup obeys exactly the same quantum rules as the qubit. In principle, it could sit in a superposition of over here and over there. The reason you never ever see such a thing is not that the rules go soft for big objects. It's decoherence, running at a speed you genuinely cannot picture.
The same leak, just faster.
Monstrously faster. Think for a moment how many photons are bouncing off your coffee cup this very second. How many air molecules are hammering into it? Billions upon billions upon billions, every instant. Each one a little witness, tearing off with information about where that cup is. So if the cup ever so much as flirted with being in two places at once, the environment would measure it, not once, but billions of times over, in a stretch of time so short it has no name in any ordinary speech. The superposition would be tagged and leaked and destroyed unfathomably faster than any clock could ever tick. That is the famous cat, if you remember the cat, the one meant to be alive and dead at once. The reason no one has ever seen such a cat is that a cat is enormous and warm and lashed to its surroundings by a fire hose of interactions. It would decohere, leak and pick one before the fastest instrument ever built could so much as glimpse it mid-blend.
So the reason the everyday world looks so sane and solid, cups in one place, coins showing one honest face, is that the universe is measuring everything, constantly, for free.
The ordinary, well-behaved, classical world you live your whole life inside is the world after decoherence has already done its work. Reality looks normal to you precisely because the environment is a relentless, tireless measurer that never once blinks. And now, feel the trap you are standing in. That very same process, the one that keeps your entire world looking sane, is the exact process an engineer has to hold at bay to build a quantum computer.
Oh, that's cruel. We're not fighting some flaw in the machine, we're fighting the thing that makes the ordinary world ordinary.
We are trying to keep one tiny corner of the universe quantum inside a universe that is furiously, ceaselessly trying to drag everything back to classical. And it gets worse, because the more powerful you make your machine, the harder that process shoves back. A big superposition, many qubits woven together into that vast web we marveled at. 2 to the number of qubits, all those amplitudes, delicately related to one another, presents an enormous surface for the environment to grab hold of. The bigger and richer and more powerful the quantum state, the more ways there are for a photon to run off carrying a piece of it, and the faster the whole thing decoheres.
So the machine grows more fragile precisely as it grows more useful. The very scale that makes it worth building is the scale that makes it hardest to keep alive.
The reward and the punishment climb together, hand in hand. That is the true shape of the problem. 2 clocks, both running down.
You keep saying a sliver of a second. Let's make that concrete. How long does a qubit actually stay itself? And what exactly is failing when it stops?
There are really 2 clocks ticking on every qubit, 2 different ways for it to die, and they run down at different speeds. Let me give you both. The first is the more obvious one. Picture the qubit up in its high energy state. Call it up. That's a struck bell, ringing. And like any struck bell, it wants to give its energy away to the world and fall quiet. Sooner or later, it dumps that energy into its surroundings and drops back down, to rest. The bell goes silent. We call it relaxation, the qubit relaxing to the bottom. And it is a kind of forgetting. Whatever you had carefully stored up there is simply gone.
All right, the bell going quiet. That one I can feel in my bones. What's the second clock?
The second is subtler, and it's usually the faster, meaner killer of the 2. Remember, the arrow doesn't only point up or down. Most of its magic lives in which way it points around the equator. Its phase. The exact angle of its swing. Now picture the qubit swinging, holding a definite phase, keeping perfect time, and the environment begins jiggling it. Not hard enough to knock it down from up to down. Just enough, through 1,000 tiny random shoves, to blur the time it's keeping. The angle drifts, the phase smears, and since the whole computation lives in those precise angles, blurring the angle quietly wrecks the calculation without the qubit ever visibly falling over.
So the first clock is the qubit losing its energy, and the second is the qubit losing its rhythm, forgetting which way it was swinging.
Beautifully put. Losing its energy and losing its rhythm. And the rhythm nearly always goes first, because the phase is the most delicate thing of all, the very easiest to blur. Together, how long the qubit can hold on to both its energy and its rhythm before the world scrambles them, that is what we call its coherence time. It's the lifespan of the quantumness, the little window in which the thing is still genuinely a qubit, and not just a sad classical bit that hasn't yet been told it's dead.
And how long is that window, honestly? No dressing it up.
Honestly? For a long, long time in this field, the very best anyone could manage was measured in millionths of a second. A qubit would cling to its quantum character for a few millionths of a second and then dissolve. Since then, with genuinely heroic effort, the finest qubits on Earth have been coaxed to hold on far longer. In some machines, 1,000th of a second, in specially cosseted systems, longer still. It sounds like nothing at all, and I won't pretend otherwise. But the raw stretch of time isn't even the number that decides your fate.
It isn't. I'd have assumed longer is just plainly better.
Longer is better, but the number that truly seals your fate is a ratio. How many operations can you perform before the coherence runs dry? Because a computation isn't a length of time, it's a sequence of steps. Each gate, each careful nudge of the arrow takes some small time to carry out. So the real question is, how many gates can you cram in before the qubit forgets everything it knew? Take the coherence time, divide it by the time for a single gate, and there's your budget. That's how many moves you get before the board is wiped clean.
And that budget, roughly, what is it?
On a good machine, on a good day, you might get some thousands of operations in before the noise overwhelms you. Perhaps, if you're being generous, tens of thousands.
Thousands. That actually sounds like rather a lot. Why are you wincing?
Because of what we asked these machines to do back in the algorithms episode. Hold that number for me. Thousands. I'm going to come back in a little while and break your heart with it. The impossible job.
Here's the obvious fix, though. I'm honestly surprised you haven't reached for it yourself. If the enemy is the environment, photons, air, heat, magnetic wobbles, then just take the environment away. Seal the qubit off. Perfect isolation. Put it in a box that nothing in creation can get into.
Yes, that is the very first thing anybody reaches for. And it is exactly right. And it is exactly where the real trap has been hiding all along. So, let's build your perfect box. We wrap the qubit away from every last scrap of light. We pump out every stray molecule of air, a vacuum emptier than the space between the planets. We chill the whole thing down to a hair above absolute zero, so there's almost no heat left to jiggle it. And that, by the way, is genuinely why real quantum computers live inside those golden chandeliers, colder than the space between the stars. We'll go and visit one properly later on. We shield it from every magnetic field. We isolate it and isolate it and isolate it until nothing whatsoever in the universe can touch it.
Perfect. And now it lasts forever and we've won.
And now it is completely useless.
Why is it useless?
Because a computer you cannot touch is not a computer at all. Think about what computing actually demands of you. You have to write the problem in, set the qubits up in some particular starting state. You have to run the algorithm, reach in and nudge each arrow precisely, over and over, thousands of times, turning it exactly this much and not a hair more, at exactly the right instant, entangling this one with that one. And at the very end, you have to read the answer out. You have to look. Every single one of those is a deliberate, forceful interaction with the qubit. Computing is nothing more than a long, exquisitely controlled sequence of pokes.
Oh no. And a poke.
A poke is an interaction. And an interaction is the exact thing we spent this whole night trying, desperately, to forbid. Every wire you run in to control the qubit is also a wire the noise can come riding in on. Every channel you open up to nudge the arrow on purpose is a channel through which the world can nudge it by accident. You cannot build a door that lets your own hand in but keeps the whole universe out. A door is a door.
So I need it perfectly sealed off from absolutely everything. And I need to reach in and fiddle with it constantly and precisely at the same time.
At the same time. That is the central paradox of this entire field, and I want you to sit inside how genuinely impossible it sounds. Perfect isolation and perfect control demanded of the same object in the same breath. Isolation says, let nothing on earth interact with it. Control says, let me interact with it, hard, thousands of times over, without a single slip. They are dead opposites, and you are required to satisfy both at once completely, or you have nothing at all.
It's like being ordered to keep a soap bubble perfectly intact in the middle of a hurricane, and also to sign your name on it. in cursive, without popping it.
That is exactly the job. That is precisely the job. And every quantum engineer alive wakes up every single morning and tries to do that one impossible thing a little bit better than they managed yesterday. Every escape hatch is bolted shut.
But hang on, hold on a moment. Classical computers aren't perfect either, are they? Bits do flip. A stray cosmic ray hits a chip, signals get noisy, and yet my laptop doesn't crumble into gibberish. We solved noise once for the classical machines. Whatever it was we did there, can't we just do it all again?
That is exactly the right instinct, and it's the very door the whole field walked up to and knocked on. So let's ask it plainly. How does a classical computer survive its noise? At heart, in one word, redundancy. You never trust one bit. You store it 3 times over. If the message is 1, 1, 1, and noise flips the middle one, so you read back 1, 0, 1, you simply take a vote. 2 of them say 1, only 1 says 0, majority rules, and you fix it straight back to 1. Copy it, check it, vote. That is the quiet backbone of every reliable machine you have ever touched.
Perfect. So copy the qubit 3 times, and whenever one of them drifts, take a vote. There, do that.
I can't. And the reasons I can't are going to swing shut, one after another, like doors slamming down a corridor. Door the first. I cannot copy it. There is a law, and we'll give it its full and proper due in a later episode, that says you simply cannot make a copy of an unknown quantum state. It's called no cloning. It isn't that we haven't yet built a good enough copier. It is forbidden, right down at the foundations, by the very same rules that hand us all this power. The photocopier for qubits does not exist, and it cannot ever exist.
All right, forget copying then. Just look at the qubit, check whether it's drifted, and if it has, gently nudge it back into place.
Door the second. And you already know this one, you just don't want to say it. What happens the very instant you look at a qubit?
It collapses. Looking is measuring. If I peek in to check that my qubit is still holding its delicate direction, I destroy the very direction I was checking on. I force the spinning coin flat just to see how it was spinning.
You would have to kill the patient to take its temperature. So the whole classical move, read it, compare it, correct it, is off the table from the very first step, because the reading itself is the damage. Now, door the third, and this one is quiet, but I think it may be the cruelest of the lot. In a classical machine, an error is a clean, tidy thing. A bit is a 1 or a 0, and an error flips it, wholesale. There are only so many ways to be wrong, and each one is obvious and total. But a qubit's error is not a flip.
Because the arrow can drift by any amount at all.
By any amount, in any direction. It can slip a hair off true, or a hair the other way, or tip a touch toward up, or a touch toward down, or its phase can creep round by the very tiniest sliver. The errors aren't a neat handful of clean flips you could write down in a catalogue and keep watch for. They are a continuous smear, an endless gradient of tiny, invisible driftings, every one of them too small to see and impossible to name. How do you even define the error when the thing can be wrong by an amount smaller than you could ever detect, in a direction you couldn't specify if you tried? And you are forbidden, on pain of collapse, from ever looking to find out.
And I don't suppose the entanglement does me any favours here.
The entanglement, the very resource, the fuel of the whole glorious enterprise, turns traitor on you here. Because the qubits are all lashed together into one great web, an error on any single one of them does not stay politely at home. It is woven straight into the whole state. One qubit quietly decohering can poison the entire entangled calculation. The way one rotten thread, pulled, can run a whole tapestry. So, you cannot copy it. You cannot look at it. The errors are a continuous, invisible fog rather than clean flips you could hunt down. And any single one of them poisons the whole. Every last tool that ever saved the classical computer snaps clean in half the very moment you pick it up. The arithmetic of the end.
You told me to hold a number. Thousands operations before the qubit forgets. And you said you'd come back and break my heart with it.
I did. So let's do the sum together, the honest one, and then we'll sit in what it tells us. Remember Shor's algorithm from the algorithms episode, the one that could, in principle, unravel the encryption guarding the whole of the internet. It was the crown jewel, the reason people caught fire over all of this. Well, to actually run it, to factor a number big enough to matter, how many of these precise little operations do you suppose it takes?
Given the way you're setting me up, I'm going to guess it is not thousands.
It is billions. On many, many qubits, all held together in delicate entanglement, you would need something on the order of billions upon billions of flawless operations, marching along in perfect lockstep, every single one of them landing exactly right.
And I've got a budget of a few thousand before the whole thing dissolves into noise.
A few thousand, against a bill of billions. And let me make it starker still, because the raw counts don't quite land the full horror. Suppose you are not merely good, but miraculous. Suppose you get each single operation right 999 times out of every 1,000. That is a spectacular gate, far, far better than the early machines could dream of. Now chain a billion of them together, every one of which has to come out right or the answer is corrupted. With an error even that small on each step, you would expect to have made something like 1,000,000 mistakes, long before you ever reached the end. Not one clean error you could spot and mend. 1,000,000 of them smeared invisibly all through a state you are forbidden to look at, riding on qubits that were quietly leaking their quantumness into the walls the whole entire time.
So the calculation is over. It's already garbage, a fraction of a heartbeat after it began. Long before the answer could ever arrive.
The noise wins the race every single time, and it is not remotely close. The qubit forgets faster than you can compute. That is the wall. And now, if you'll let me, I want to lay the whole grim thing out plainly, all in one place, because it deserves to be looked at squarely rather than softened.
Go on, say all of it.
A qubit is powerful only because it is delicate. Its delicacy means the environment measures it constantly for free. The same relentless measuring that makes your whole ordinary world look ordinary. That measuring, decoherence, leaks the quantumness away, one stray photon at a time, spoiling the interference the entire machine runs on, turning your sculpted answer back into a wash of noise. To stop it, you would need perfect isolation, but perfect isolation makes the machine untouchable, and a machine you cannot touch cannot compute. So you must also have perfect control, which is the exact opposite thing, and every wire of control is a wire for the noise. And when the errors come anyway, as they always do, you cannot copy your way out, because copying is forbidden. You cannot check your way out, because checking is destroying, and the errors are not even clean flips you could hunt, but a continuous invisible fog that any single slip spreads clean through the whole entangled web. You get thousands of moves. The dream needs billions. By every honest reckoning we have laid down tonight, a useful quantum computer should be impossible.
And that's where we are. That's the bottom of it.
That is the bottom of it. And for a while, I mean this, for a real and a painful while, a great many brilliant people looked at precisely this chain of reasoning, exactly the one you and I just built, and concluded soberly that it was over, that the whole gorgeous idea had been a mathematician's daydream, beautiful on paper and flatly forbidden by the world, that you could prove the lovely theorems all you liked, but you would never, not ever, hold this machine in your 2 hands, because the universe simply would not permit a thing this delicate to survive being used.
It really does look dead, doesn't it? Everything we built across 6 whole episodes, the qubit, the interference, the entanglement, the algorithms that put every secret on the internet on a countdown clock, all of it runs on a quantum state. And the quantum state cannot survive contact with reality. The engine is perfect, and it melts the instant you turn the key.
The engine is perfect, and it melts the instant you turn the key. Sit with that tonight. Don't rush past it, because this is the true low point of our whole story, and it would be a lie of mine to hand you a comfort before you felt the full, honest weight of the problem. The most sensitive machine ever conceived by anyone, drowning in a universe that will not for one instant stop touching it. The pin.
And yet, here you are, sitting across from me, teaching me a 12-part course about quantum computing, which means you don't actually believe it's dead, or this would be a very short and a very sad little series.
You've caught me. No, I don't believe it's dead. It isn't dead, but I made you a promise at the very start of this season that I would never once tuck you in with a comfort you hadn't earned. And I mean to keep that promise tonight, of all nights. Because the way out of this, and there is a way out, I give you my solemn word, is so strange, so wildly against everything your gut is shouting at you right now, that if I simply blurted it out this minute, you would not believe me. You'd be sure I was cheating.
Then give me the shape of it at least. 1 pin. You always leave me 1 pin.
1 pin, then. Everything tonight told you the very same thing. You cannot protect a quantum state, because to protect it, you would first have to look at it, and looking destroys it. So here is the shape of the impossible thing that saves us. What if you could find and fix the errors in a quantum computer without ever, even once, looking at the information you were protecting? What if you could spread a single precious qubit's worth of meaning out across a whole crowd of ordinary physical qubits, so cunningly that you could interrogate the crowd about its mistakes, hear exactly what went wrong and precisely where, and still learn absolutely nothing about the secret they are all, together, holding?
Fix a mistake in a message without ever being allowed to read the message.
Without ever reading it. It sounds like a flat contradiction. It sounds every bit as impossible as everything else we buried out here in the dark tonight. And it is the single most beautiful idea in this entire field, and it is real, and it is the whole reason you and I still have 6 more episodes left to spend together. But you have to walk out into the dark tonight, because you haven't earned the light yet. Tonight, the enemy wins. Tonight, the dream looks dead.
The most sensitive thing we know how to build, inside a universe that never once stops watching. And somewhere on the far side of all that, a way to guard a secret you're forbidden to even look at. I am going to be up all night with this one.
Good. Be up all night with it. Because next time, we do the impossible thing. Next time, we fight back.